Absolute value functions. Our objective is to graph and transform absolute value functions. Who uses this? Park rangers can use absolute value to monitor the movement of an animal as it passes a specific location. Let's look at the absolute value parent function. So your domain is all real numbers, and your range is are all your non-negative real numbers. Well, that makes sense because your absolute value of any number is the distance from 0, which has to be positive. So if you put an input of -10, it's going to give you positive 10. Input of -5, it's going to give you positive 5. 0, 0, 5, 5, 10 is 10. So basically, it's going up at a rate of up 1 over 1, up 1 over 1, if you want to think of it that way. But either way, when you make a table, that can also help you with this. So your parent function starts at 0, 0, just like almost every parent function. And then we have it going up at a nice rate to the right and up at a nice rate to the left. So it makes a nice V. So your absolute value parent function is a V. So now let's get g of x. Let g of x be the indicated transformation of f of x equals the absolute value of x. So write the rule for g of x and graph the function. In previous videos, we've talked and learned about how to transform functions to move things up, down, left, right, stretch, and compress them. Well, we're going to do the same thing, just with absolute value functions. So we want to go 2 units up. So if you have g of x equals f of x plus k, because we're going up, so it changes your vertical, which is going to end up changing your output. So you're going to add to the entire function. Well, what was f of x? It was just x. So x plus 2. That would be your new rule. And then we need to graph its function. So you take exactly what you did for your parent function and just move it up 1, 2. So 1, 2. Up 1, 2. And there you go. Alright, so this time we're going to go 3 units left. So to go 3 units left, you have your parent function of f of x equals the absolute value of x. And then we want to translate this to the left 3 units. Well, keep in mind that when we're transferring things left and right, that's going to be changing our input value, so it goes with our x value. So it's going to go inside with our x. So it's f of, and then x minus h is always in the form of a minus. So if we're going to go to the left 3 units, it's like saying minus -3, which you can also say is x plus 3. So you're going to have a vertex at -3 because we went to the left 3, and nothing else about this graph changed. So it still goes up to the left and up to the right in the same manner as your parent function. It just has moved to the left 3. The vertex of an absolute value function. So the graph of g of x equals the absolute value of x minus h plus k is the image of f of x equals the absolute value of x after a horizontal shift of h. So remember, h is going with your input value, so it changes your horizontal because x is your horizontal axis. And then you have a vertical shift of k units. So k, vertical, up and down, so it changes your output, which is the whole thing. So you take your whole thing and you add on k. So therefore, your vertex is going to be at hk. So let's look at translations of an absolute value function. So we're going to translate f of x equals the absolute value of x so that the vertex is at -5, 3. So let's start with the idea. Okay, so we have g of x equals the absolute value of x minus h and then plus k. So k is your vertical, h is your horizontal. So now if we go, we've got g of x equals the absolute value of x minus our negative 5 plus our value of 3. And we can rewrite this as g of x equals the absolute value of x plus 5 plus 3. And then when we graph, nothing else has changed. It hasn't stretched or compressed. All it's done is take the absolute value function of its parent function and just move it to negative 5, 3. So everything else remains. You've just taken the vertex and moved it. So now let's try transforming absolute value functions. We're going to perform each transformation and then graph it. So now we're going to basically work backwards a little bit. Okay, so since we're trying to reflect it over the x-axis, since it's going across the x-axis, your y is what is changing. Because if you think your x-axis is here, and if it's flipping from here to down here, you're flipping over it and your y is going to change. So therefore, your negative sign, because we're reflecting, so we're going to use a negative, is going to be to the entire function. So you can think of it as g of x equals negative f of x. So now if we substitute in whatever f of x was, which was this here, we will have our new function. So we have g of x equals negative the absolute value of x plus 2 plus 1. And it's the negative of all of that. So then we can more or less distribute everything across, which would help you so that way you know that your vertex is going to be at negative 2, negative 1, because it's going to change that to a negative and that one to a negative. So your vertex is going to be here. So since you have your vertex here, we can now plot your point for your vertex, and then since we're reflecting, you're basically going to have the same graph as you did, only it's going to be reflected across your x-axis, so it's going to be upside down now. Let's try another one. So we're going to perform this transformation and then we're going to graph it as well. So we want to stretch the graph vertically by a factor of 3. So we're going vertically by a factor of 3. So when we're dealing with something vertically, we're multiplying the entire thing. So you can think of it as g of x equals our a times f of x. Well, our a happens to be 3 and our f of x happens to be the absolute value of x minus 2. So our g of x is going to look something like this for right now. So we have g of x and we have the absolute value of x minus 2. Let me fix that parenthesis there so it looks a little bit better. Okay, so now we can distribute. So we have g of x equals 3 times the absolute value of x minus 6. So when we graph, we have it starting at negative 6, and instead of it going up 1 over 1, it's going to go up 3 over 1. Up 3 over 1. So you can think of it as just your slope. So when it's by itself, it's up 1 over 1, up 1 over 1, which would be a rise of a slope of 1. But now our slope is 3, so it's up 3 over 1. So let's try this next one. This time we're going to compress the graph horizontally. So if we're dealing with something horizontally, it changes it inside with the x because it's our input that changes. So you can think of it as g of x equals f and then 1 over b times x. So that's the other thing. When we're compressing something or stretching something horizontally, it's not just the 0.5, it's 1 over b. So it'd be 1 over 0.5. So that leads us to our g of x equals the absolute value of 1 over 0.5 times x minus 1 and then minus 3. So we just took this right here and we stuck it all in there. And now we can simplify. So 1 over 0.5 is the same thing as saying 2. So we have 2x minus 1 and then minus 3. So when we graph, our vertex is going to be at 1/2 and negative 3. As if you add 1 to both sides, like think of this as a separate little entity here, equaling 0. So you're going to add 1 to both sides, then divide by 2. So therefore your x is 1/2, and your y is going to be negative 3. That's like your y-intercept. And then you rise and run. And that ends our lesson on absolute value functions.